Ladies and gentlemen, it's 4:42 at my watch. I think it's time to start. As far as I'm concerned, I'm particularly happy because all my speakers are here. Unfortunately, there are many people still around, and so in the meantime, I just take the floor so that people outside will realize quickly that we are kicking off. Can you hear me now? So when it's red, it means that it works. Okay, here. Okay, very good. So let's start. The only person that I cannot see now is the facilitator. Where is Biagio? Okay. Anyway, he will, and he's also the rapporteur. So he's the one who is supposed to take notes and eventually, at the end, report on what it has been said. So first of all, why you are here? You are here because you are expected to be hopefully wiser at the end of the panel in relation to the implications on, as far as the CCAM, implications on road transport energy intensity. In case you are here and you expect to know everything about overcoming barriers to CCAM deployments and so on, it means that you are in the wrong room. So the right room for this kind of issues is the room which is on the ground floor, just on the right-hand side. So here we will be speaking about energy. Energy intensity in CCAM applications. My name is Andrea Gentili. I will have the privilege to moderate this session. I work for the Commission, the DG Research and Innovation in the unit dealing with all transport modes, so automotive, aviation. So we do research and innovation. We deal with research and innovation for all the transport modes, including, of course, automotive. All right. I also lead a task force on partnerships in the Commission. So, I have the task to make sure that the Commission representatives in the different partnerships, they are saying the same things. One voice. The Commission is one services. Independently, if it is RTD, of course, if there are elements more towards RTD or MOVE and so on and so on. Okay, but this is just so that you know me a bit more. Why energy intensity? The colleagues from JRC have conducted an interesting study in relation to the energy intensity of a CCAM application. And they will present first one case study, which is an urban application in the cities. And then there will be another section later on dealing with the case studies on highways, extra-urban. So, okay. So those are the two. So you will get 15 minutes presentation, and I will be quite strict. 15-minute presentation from our colleagues in JRC presenting the first study. We will have exceptional speakers discussing each of the two studies. 3 speakers, 3 panelists for each. And then I will try to tease our speakers because our objective, my objective today, is to make sure that you go home with in your country, in your organization, at the end of the conference, with at least one good idea that you have collected from the discussion. A good idea which hopefully could be transformed into action. You will go home and you have the intention to do something. All right, let's go first. So I would like to call on stage my colleague Ada Garus. Ada works, as I said, at the JRC, part of the European Commission, and she conducts research on the environmental and systemic impacts of new mobility solutions. And she was responsible for the urban case study that I mentioned in this, in the context of CCAM energy intensity assessment. A big applause for Ada.
Thank you, Andrea. And thank you all for coming to the session. So, let's see if the clicker works. Yeah, great. So, to understand the implications of energy, we first needed to understand what types of implications on energy we could see with development of automated mobility. And we classified it into 3 categories. So first, we see a direct impact on energy consumption due to the automated systems and the technology that is required for automated driving. So this includes everything from sensing, processing, data transmission, and off-board infrastructure. Then we see the impact on driving itself. So with automation, driving could get smoother. We could also have eco-driving benefits because of better speed compliance, which would reduce energy use, and smaller time gaps, especially on highways, which could then lead to better traffic flow and lower energy consumption. And then we have the third category, which is indirect impact. So in a way, the automated mobility could impact the travel behavior because of more convenient travel, more productive, more comfortable. It could lower our value of time. It could introduce new services, shared services, and then lead to mode shifts. So, for example, people switching from walking to automated mobility or from cars to automated mobility. So these are the 3 aspects that we identified. And then this is the framework which we followed. So first, to understand how we can quantify this, we started with literature review. Then we classified the vehicle tasks, the tasks that the vehicle needs to perform to drive autonomously. And from that on, we conducted a workshop with CCAM members of the CCAM Partnership in March 2024 here in Ispra to validate our approach. After the workshop, we also conducted interviews with key external market players. And from then on, we started to refine our approach again with the CCAM members. And so the work is based on 3 data sources: literature review, the workshop with experts, so the contribution of the CCAM partnerships, and also information from the external companies and partners. So what we can see here is the first pillar of the energy impact. So the energy consumption of the technologies that enable automation. And we have 4 configurations because we are, of course, not sure how automation will look like in the future. And first, let's start with the prototype configuration, so what we currently could have on the roads. So what we saw is that there is full sensor redundancy, so we have LiDARs, radars, multiple cameras, and high onboard processing load that could sum up to 2,000 watts of power. Plus off-board energy for tasks like HD map updates and video storage. And this represents the early stages. Then we have the enhanced sensor configuration, and this reflects more mature market-ready systems. It uses a reduced and optimized sensor set, keeping the safety intact, while lowering onboard consumption to 860 watts. And communication and storage are also more efficient, cutting overall energy demand by more than 50% compared to the prototype. And then we have the third configuration, which is a bit different because it's the vision only. So the car would rely only on cameras with no lidars and radars. So of course, again, the onboard consumption lowers to 390 watts, but it's still uncertain whether the industry will move in this direction at scale due to current concerns about the reliability in complex environments. That's why the final configuration, the future configuration that we could envision, it's based on the enhanced sensor setup. It assumes next generation sensors, edge computing, AI-driven data optimization, and more efficient communication protocols. And combined with smarter off-board infrastructure, so better data compression, hybrid storage, energy-efficient cooling, this setup could reduce the energy consumption of the automated kit by 80% compared to the current prototypes we have today. And so in the urban case, we focused on the indirect impacts of introduction of automated mobility. And we used an agent-based model to do so because it enables to represent individual mobility choices. And we used Sim Mobility Framework, which is there on the right-hand side of the slide. And it's basically a chain of discrete choice model that reflect how people make travel decisions. First, they decide whether they will travel at all that day. Then they decide for what purpose, how many trips, which modes, where to, which time. It also allows to generate a stop on the way. And once we had all those travel patterns for every agent in the simulation, we implemented them into AIMSUN, which simulates the traffic flow and allows to estimate the energy consumption. And as a case study, we used Santander, which is a city in northern Spain with 172,000 inhabitants. And to estimate all those discrete choice models, we used the data trip diary from more than 1,000 people that recorded their trips for more than a week. And I will not go into too many details here, but I will link the report at the end. So just to summarize, we wanted to understand exactly how the automated mobility could be implemented and what could that entail. So we had a lot of scenarios. We had the baseline, which reflects the travel behavior of people from Santander today. And then we model 4 types of AV deployments. Robotaxis, which are smaller vehicles which can be shared or private rides, and can fit up to 4 people. Then we had automated shuttles, which are larger and always shared with capacity of 15 people. More frequent buses, which would be automated, and that could mean that buses in Santander could run more frequently, but the assumption is that they keep the same network. And what would happen if the AVs were privately owned? And we also included several policy and system-wide scenarios. A UVAR scenario in which the center is strictly pedestrian, a scenario where no private cars are used, and this was to to explore mode shifts under extreme condition, a congestion effect because Santander is not congested, and we wanted to see what could be the results in a congested environment in a more constrained network. Car dependency reduction strategies such as fewer lanes, slower speeds, and limited parking that would discourage private car use, and a case in which privately owned AVs drive someone somewhere and then return home to serve other household members or to simply park there. Finally, all the scenarios have a key assumption that all the vehicles, automated and non-automated, are electric. And we did that to capture the effect of automation and not the effect of electrification of the fleet. And here we can see the first results. This slide shows how automation influences the distribution of transport modes. We observed that the introduction of robotaxis And shuttles leads to a shift away from walking and public transport, especially in the case of robotaxis, which are more attractive, flexible, and so on. Importantly, we don't see a major drop in private car use unless external regulations are applied. Simply adding AV services doesn't cause people to give up their cars. When we introduce the UVAR, the effect is limited. But when we simulate broader measures like reducing the car lanes and so on, we see a much stronger reduction in car use. So while automation brings new mobility options, policy plays a key role in shaping how people respond to those. And since you are here for the energy information, this slide represents the daily energy consumption for the city of Santander for the prototype configuration, while the automation is still in the early stages of development. So in the worst case scenario, we see that the energy consumption can actually triple because we have private AVs which go somewhere, drop off the passenger, and then return home. So because of the extra mileage, we see a considerable increase in energy. But even without this extreme scenario, the rollout of robotaxis could double energy consumption because of the early stage automation energy requirements, which sum up to 18% of the total energy demand. Shuttles are a bit more efficient as they support higher occupancy and shared trips, reducing energy per passenger. However, the increase is caused by two things: the energy consumptions of the vehicle itself, as well as the mode shifts, and especially the mode shifts from more active modes towards the usage of cars. So under early configuration, we could see the increase in energy consumption. However, if we look at the future, which we will do so now, we see that the effect is much lower. So technologies such as more efficient sensors, edge computing, communication protocols could already cause significant gains. So in the robotaxi scenario that I was talking about before, comparing the prototype and the advanced technology scenario, the reduction of energy between them is 15%. So just optimizing the technology has a meaningful impact here. But the biggest effect comes when we combine technology with supporting policies. So in scenarios which align with the current European city strategies to reduce car dependency and promote shared services, in this case the shuttles, we can achieve, in fact, 20% reduction in energy consumption as compared to the baseline. And this shows that automation can reduce energy consumption, but it's not guaranteed. Without the right policies and technology improvements, the opposite can happen. So ultimately, it's not just about deploying AVs, it's about how we deploy them. Here are some key takeaway points, but I already mentioned them in the presentation. So I just want to leave you with the thought that context matters. It's a result from a middle-sized city in Spain. And of course, these results could be much different for car-dominated or congested environments. Also, further research is needed because public transport in Santander is limited. Further research would be needed to study how AVs can actually complement public transport instead of fighting against it. Thank you.
Thank you very much, Ada. Don't run away, in case there are some clarifications, questions, or if otherwise. I think Ada is here. You can also ask her during the coffee break. Huh? I cannot see. Very good. You have been great. Very clear. Thank you, Ada. Now, I would like to invite our panelists, the first group of three, to react on what they've seen. So the first panelist is Batain Namiasbiran. I'm sorry. I think it's pretty well. She's a senior lecturer at the School of Mechanical Engineering at Tel Aviv University. and in Israel, of course. And she's also visiting professor at C4 here, Energy, Mobility and Climate here at the Joint Research Center. The second in a row is Dimitrios Milakis, European Research Coordinator at the Institute of Transport Research, DLR, and also co-leader of the Cluster 6 Societal Aspects and People Needs of the CCAM Association, with, of course, a research focus on transport innovations and society. And last but not least, the third one, Christian Scharnost, Director, Automated Driving, member of Cross-Domain Computing Solutions Division at Bosch, Germany. He has been appointed to the role of the CCAM Association Vice Chair until recently, from 22 until December 24. So I would like to ask my speakers, and you will be the first because you are in the middle. 3 minutes reactions, only 3 minutes reactions of what you heard.
This is on, right? Okay, so first of all, I think it's a very good and very important research. The results show how much on-board and off-board and communication is important to include in energy consumption estimation. And until now, most, if not all, the large-scale evaluation that we are performing are neglecting or assuming such energy consumption is neglectable. And Ada perfectly showed that this is just not true, and we cannot neglect it anymore. And if I want to address former studies that were done by my group and together also with the team here at the GRC, I can say it can be generalized. I mean, the results that Ada showed are very true to mid-size, low-intensity cities. And for example, for cities in America where we studied similar scenarios, we showed that the results, for example, in that reflected in an additional or the share of automated vehicle will be a bit moderated than what Ada showed. And this is because the place of walking in such city as Santander, which is unique. So as more you have active modes, and Ada said that as well, walking and cycling and public transportation, the more room you have for AV to penetrate. And this is quite dangerous. I mean, it should be restricted. And we can come up with supporting policies to make sure it doesn't happen. If I want to address, let's say, to reflect what will be the results in very dense and high, with very developed public transportation, for example, systems such as Spain, maybe Madrid, Singapore, these kind of cities that are very dense and populated, then the room of AB will be much smaller, and so the energy consumption as well. Because, again, public transportation is dominant in the environment. Thank you.
Thank you very much. Good points. Dimitris, you are the next.
Sure. I second, actually, your point that the key contribution of this study is the integration of the exploration of the urban context, the highway context, the on and off-board system, and their energy consumption. This is, I would say, an added value to the literature of what we know so far. The For the urban context that we discuss here, the more specific contribution is that several deployment models were assessed coming from robotaxis, shuttles, buses, as well as the private automated vehicles, and these were assessed across different scenarios, policy scenarios. And this was not assumptions of a team that did some desk research here at GRC isolated, but they connected with the stakeholders, and therefore their assumptions are validated, which is not often the case in studies. Scenarios are developed usually by the researchers, and I'm glad that Christian facilitated this integration from the CCAM Association, so you have this very elaborated integration. Coming to the outcome, first let me say that it is indeed also aligned with my own personal research, the research that I'm aware of globally, and it's a very strong statement. When it comes to energy consumption, technology is not the only factor, or maybe is not the important factor. What is important is the deployment model and the policies that accompany the deployment. Not necessarily the policies that are related to CCAM, but policies related to reduction of car dependence. So these are the two key messages that I take. And the bold statement was that you see increase across almost all scenarios, except for the scenario that you have shuttles with very restrictive policies. So we need to keep this in mind. In all other scenarios, you get more congestion and you got more energy consumption. So concluding, the message is be clear with the deployment model when you consider energy consumption from this perspective. From other perspectives, you might think differently, but from energy perspective, be clear with your deployment model, shared, not solo sharing, not like Waymo-based or to refer to very specific deployment models, but shuttle-based and bus-based, accompanied with clear policies, both on the supply side, so to support this deployment, but also on the demand side, so demand to help demand shift towards these vehicles, so they are, so the energy consumption is lower. By the way, I was thinking also that this also could help the economic viability of such use cases, since you shift customers from one side to the other. So that's in a nutshell. Thank you.
Thank you. So what is your perspective, Christian?
So firstly, it's a relief in two aspects. It's a relief because I believe together in a common approach, we were able to close a gap in terms of when we started, there was no study available, and we reviewed the environment carefully, that would fulfill all the prerequisites that we had when it comes to describing the effect in a scientific way, in a fair way, in an unbiased way, in a way that we could trust in for the European constellation. So actually, the impulse came in 2023 with a study from the MIT, a very reputable organization and institute we are all aware of. But when we carefully read that and were asked, hey, you CCAM guys, what do you think about this study? Well, not quite. We should do better. And while we are focusing at the CCAM, at the advantage of the automated driving technology and emphasis on safety, of course, and looking at the quality of life aspects that could be enhanced with this technology, we frankly had to say, hey, when it comes to side effects like energy consumption aspects, we were walking on thin ice because we had no study. And it was then in November 23 when we kicked off this study, found with the JRC team a capable team that had the capacity, both time-wise as well as know-how-wise, and also the reputation to start the endeavor with an unbiased and fact-based approach. And we accompanied this study over the last 1.5 years, and we had quite a bit of disputes and debates, but with respect for each other. And that enabled, I believe, a result that the CCAM can subscribe now. And we had also the members involved, so had a review on a broad base as well. And at my side, luckily, I had 2 experts, Simon Edwards and Peter Urban from University Aachen. And they really guaranteed the quality of the study methodology-wise and also in terms of consistency of data inflow.
Thank you very much. It's important. The journey is important. How the study was conducted. Thank you for pointing this out. Any questions? Any comments from the floor? In the meantime, if you, panelists, you want to make a comment to each other's statement. Like in the European Parliament, by the way. Battery law, okay? Yes, please do it.
So, Christian, you talked about relief. But, I mean, do I understand correctly that we still need to pay significant attention to the topic of energy consumption of the technologies? Because as far as I could understand, although it wasn't totally clear, the assumption is that we're still going to dramatically reduce the energy consumption of the technology. So we do need to have this as one of our priorities and basically keep track of where we're going with the technologies in terms of energy consumption. Is that a correct understanding, interpretation of what we saw?
Christian?
Thanks, David. So, yes. So on the one side, there will be a progress in terms of energy-saving technology when it comes to CCAM. Anyhow, why that? Because when we talk about the urban context and also the ambition to reduce CO2 by getting off the internal combustion engines, we are talking about battery with a battery capacity that has a restriction. And when using too much of these energy-sucking devices, then you automatically reduce the driving range of the vehicle. So it's the ambition, of course, of all vehicle providers to provide a value for consumers, being in competition with others. So they are very eager to reduce all parasitic energy consumption aspects. So that's the automatic thing. The other thing is that also cost-wise, it pays off to reduce the energy consumption because these systems will be more efficient. So in this sense, it's a relief now that we have a clear direction and that we get a clue how to apply this technology. So what in terms of regulation is helpful, is needed, and with a lot of technology, you can do good things and bad things. We are close to a nuclear power installation here, research. So we all are aware with technology, you can do both. And I believe we have now a better direction and a clearer focus and target how to apply and giving advice to policymakers as well.
I think one question there.
It's working, thanks.
Can I have a comment before the second question on this particular?
Yes, okay.
That's an important question, but let me put things into perspective. The total energy consumption by the onboard and offboard systems at the prototype session, please correct me if I'm wrong, is 18%. And this is expected to be minimized, so to be almost negligible when the sensor and computing systems are further optimized. And what is also interesting is that the shuttle energy consumption and the robotaxi will become more or less the same, I mean, the onboard and offboard system consumption. So again, it's, in my view, what I read is not about the onboard and offboard. Yes, we need to, we cannot simply ignore this. We need to keep investing to make it better and more optimized. But the bulk of energy consumption comes from the deployment model, simply saying that the higher the occupancy, the lower the energy consumption per passenger. That's a simple equation. And this is what the study says, according to how I read it.
Yeah, thanks, Francisco from ITEC Spain. Only one remark, because from the study we can understood that automated vehicles are very bad, eco-friendly, and we should not go in this direction. We must not misunderstand, if I am right, emissions, energy consumption with CO2 emissions. So this is only remarking, the study is remarking that we need clean energy generation. That's it. Energy that comes from clean sources. But it is nothing to be alerted that it will be very dangerous for the environment. Only this remark, it seems obvious, but I think that it's important to highlight this at this point. Thanks.
Thank you very much. Indeed, the study is supposed to be publicly available from today or tomorrow or the day before, so you will have access to the full document. Any reactions? Otherwise, I would like to wrap up because we are already running late, as usual.
Just one quick, yes, I agree. If the energy grid is green, yes, I agree. But still you have grid problems if you have energy consumption at high levels. So we still need to take care of the amount of energy we consume.
I'm also very quick. So, yes. So clearly, and I said it before, onboard, off-board communication energy consumption is significant. It will be significant also if we work to make it much more efficient. It will account for something like 5 to 6%. It is significant. Therefore, it should be included in all study large scale that we are doing. And that's it.
Who's next?
So I believe that we should continue the research in terms of answering the questions that remained unanswered. So whenever conducting a study, you come across new questions you were not able to raise before. So one existing gap is that applies for the urban scenario, to look for efficiency gains by V2X communication and traffic streaming, so traffic management. That is something we will see in the presentation of Costas for the highway case, and for the urban it was, in terms of availability of data, not possible, but to simulate the results for Brussels, for example, that would be very valuable.
Thank you. Dimitris, the last word.
Last word. Policy is important. So what I take with me on my luggage is that I need to work harder together with my colleagues at DLR to finish our report on the policies supporting shared automated vehicles, both from supply and demand side. And what we are saying is that maybe a policy shock is required.
Join me with a big applause for our... And now we move on to the second section. It's on highways, extra-urban. My colleague from JRC, Costas Mattas, is already here. Costas conducts research on the impacts of automated driving systems and was responsible for the case that he will present to you. Costas, the floor is yours.
Thank you very much. Thanks a lot, everyone. So this is the highway part, and for the highway, our simulations were based on a model of the ring road of Antwerp in Belgium. And what's important to notice is that all scenarios that we simulated had a duration of 3 hours, with the first and the last hour having a low demand, being a loading and unloading the network, and with the second hour being the hour of the much interest, as we had the rush hour traffic for the specific simulated network. Now, the vehicles that we have been simulating are of 3 categories according to their driving technology. We have simulated manually driven vehicles for which we used AIMSON, but we had to model our own, to put our own custom behavior models that we, for the human drivers, calibrated based on data from the HIDI dataset. So actual trajectories from highways in Germany using Python and calibrating on macroscopic values. Then we have the ACC vehicles, and the ACC vehicles are representing the low level of automation of ADAS systems that are currently available in the market. And for those, it was similar models as with the manually driven vehicles. The difference is the car following model, for which we used a linear model with parameters taken from the literature, from studies calibrating on actual systems that are available in the market. And finally, we go to the AV vehicles, where we based the systems, the simulation on the models that we used for the ACC, but we had some specific assumptions about the differences between the ACC and the AV vehicles. And for these assumptions, the workshop with the experts was very, very useful for us to have valid assumptions as mentioned by the panel earlier. So the most basic, the first and the most basic type of AV is this AV basic, and there is 2 major differences. Firstly, the distance to the leading vehicle, counted as a time gap in seconds, is considered to be a little bit lower from 1.2 seconds to 0.9 seconds. The second and even most important difference, what we got from the experts of the industry, was that automated driving systems are expected to have a perception and understanding of the traffic state around them. And based on this understanding, they could be able to do predictions and take actions based on those. Now, instead of modeling every and each aspect of this behavior and simulating it explicitly, we went with simulating this predictive and fast-reacting behavior by decreasing slightly the reaction time from 1.1 seconds, that it was for the ACC systems, to 0.9 seconds. The only specific behavior that we did explicitly model was multi-anticipation, which means that for AVs, the simulated AVs react to two vehicles in front of them and not just one. Then we had specific additional capabilities that we tested separately. The first one was connectivity. Again, according to the workshop that we had with experts, we found two applications that were considered to be the most reasonable to test. The first is V2V and its platoons, limiting to two vehicle platoons and limited to heavy-duty vehicles, so trucks. The second connectivity application that we tested together was V2X, and it was vehicles getting information about the speed, so the traffic conditions, 4 kilometers in front of them. Then we had the case of AVs with even lower reaction time. The assumption here is that possibly those AVs will have so much better perception and prediction capabilities, and the reaction time, it makes sense to be simulated with an even smaller value of 0.5 seconds, which is still reasonable and realistic. Then we had the speed compliance scenario, where the AVs are all abiding by the speed limit. This one we tested separately just to see what's the impact of this separately. Another capability is the stable AVs. So what we know for ACCs is that very often they have a behavior that destabilizes somehow the traffic flow, mimicking some of the human drivers. We also know from the literature that using the same models and calibrating them a little bit, we can have a behavior that's stabilizing the traffic flow, and this is exactly what we tested here. Finally, we have the AV full scenario where we have the AVs with all the discussed capabilities. Now, the scenarios that we have tested fall in three major categories. We have tested scenarios where all vehicles in the network are driven by the same technology, so 100% penetration rate. Those could be manually driven vehicles, ACC, and so on and so forth. Then we have scenarios with mixed traffic, and the mixes that we tested were only manually driven vehicles and AV full, and also ACC systems and AV full vehicles. Finally, we tested two scenarios only with increased demand. So for AV basic and AV full, we tested with the rush hour trips being 10% more. Jumping to the results on the traffic flow side, we see here the average speed in the network through time. With the green line, we see the manually driven vehicles, which is the baseline, and we see how it starts uncongested, and then the speed drops with congestion. The red line, representing the ACC vehicles, shows how this deterioration, this unstable behavior, deteriorates the traffic flow during congestion, and that the average speed drops even lower. However, with only the small modifications of the AV basic case, we see how the traffic conditions are getting better, and the recovery to the free flow conditions is happening much faster. Now, for the rest of the scenarios that we tested, all of them had some beneficial impacts, with the best one by far being this one, the blue line, which is, of course, the AV full case. And what we see is that for the uncongested cases in the beginning and the end, the speed is a little bit lower than some of the other scenarios, and this is because, of course, they abide by the speed limit, so you don't have vehicles overspeeding. But most importantly, during the congestion duration, you see that the average speed never drops below 80 kilometers per hour on average, and that the recovery to free flow happens almost instantaneously. Now for the mixed traffic scenarios, on top we have the mix between manual vehicles, manual-driven vehicles and AV. And what we see is that increasing the penetration rate of AV full simulated vehicles, the traffic conditions are getting better. There is an important point around 40% penetration rate where we see that the speed profile is smoother. We don't have these sharp drops that could indicate dynamic congestion phenomena that are emerging. And after this 40%, we still have benefit with more AVs introduced, but there is a case of diminishing returns. For the AC system case, this happens a bit higher with 60% penetration rate of AVs. This is because the traffic conditions are deteriorating with this simulated instability of the ACCs, and we need a little bit more of the penetration rate of AV full to balance out this behavior. Now, for the additional demand, what we see is that both for the AV basic and AV full, we have some deterioration in the traffic flow comparing to the same case with the same demand. However, what we see is that with the same infrastructure, without changing anything in the road network, the infrastructure can accommodate more trips, more demand, having similar traffic conditions as the baseline. Now let's go to the important energy results. And the first and important thing to note is that indeed the propulsion energy with the blue color is by far the most important factor. And those y-axes are starting with 1 because there is for each and every one of those cases 1 megawatt hour is for propulsion. And we are just zooming in here for better readability. So indeed propulsion is important. And for propulsion, we see that the ACC vehicles, of course, with this deterioration of traffic flow, increase the energy requirements for propulsion. And all the AV cases that we have tested have been decreasing, even if it's just marginally, the energy required for propulsion. However, when we also consider the energy for the automation kit, then this image changes a little bit. For the automation kit, the most important that we found was with the red color, the sensing and onboard calculations. And what we see overall with the results comparing to the baseline is that for the prototype configuration, in all of the cases, we had some negative overall impact in the energy consumption. We need at least enhanced sensor configuration, which is of course something that we should expect, to start seeing some positive balance in the energy, energy-wise. Now, even for the best assumption for the automation kit, the advanced technology optimization, we see that not all of the AV cases are really giving us a benefit energy-wise. So we understand, first, that the automation kit indeed should be optimized, and it's an important factor, but also the automated driving systems should be designed in order to improve traffic. Now, for the mixed traffic, we have some also very interesting results. We see here the mixed traffic between AV and manual vehicles. And as you may remember, for the prototype configuration, which is the more intensive, energy-intensive vehicles that we are not really expecting to have in full deployment, for 100% penetration rate, indeed, we have a higher energy request. However, for 20 and 40% penetration rate, so for the smaller penetration rate, we see some energy benefit. What happens here is that we are introducing energy-intensive vehicles, but those vehicles are improving the traffic conditions, giving a benefit to the rest of the traffic flow. And in the overall balance for the whole network, for those low penetration rates, we see a benefit. However, this comes as a positive externalities, and it's not really a benefit realized by the users of those AV full cases, at least for the prototype configuration. So, to conclude with the main points we need our AV systems for the highway at least to be designed to improve traffic flow in order to realize the best positive impacts. And if it is so, the positive impacts could be realized even for small penetration rates. Moreover, this improvement in flow means that in some cases, the same infrastructure will be able to accommodate many trips. But in all these studies, another significant factor is not just the technology and the behavior of the AVs that we're introducing, but the technology and the behavior of the existing vehicles. Now, energy-wise, we see that optimization of the automation kit is something that we have to keep in mind, as discussed also for the urban case. What we have also seen, and you can see it also in the report that I will link in the next slide, is that with the increased demand that we were able to accommodate, of course, comes increased energy demand for the network, energy consumption. And we have found a very interesting case of those positive externalities and potential equilibrium phenomena that we might need to investigate a little bit further. Thank you very much. This is the QR code for the report, and you are more than welcome to reach out to us if you have any questions also afterwards. Thanks a lot.
Thank you. Thank you, Kostas. Any questions? Any request for clarifications, or everything is clear? Okay, it seems you've been effective.
Thank you very much.
Very good. Another big applause for Kostas. And now I would like to call next to me the three panelists of today. I start with Alina Aitoniemi. She's a senior scientist at VTT, well-known research centers in Finland. Recent work includes assessing energy use, emissions, travel time impacts of automated passenger cars on European motorways and urban roads. She's been working in the project L3 Pilot, HI Drive, and also involved in the common evaluation methodologies for CCAM, the famous FAME projects. Okay, the second, we have Christian Merkt. Christian is Director, EU Governmental Affairs, Digitalization and Automated Driving at BMW. He's also the chair of the CCAM Partnership. And finally, last but not least, here we are, Vincenzo Punzo, full professor in traffic simulation, management and control at the University of Naples. Federico II. Okay, my dear panelists, we would like to hear your reactions, comments on what you just heard. The rules apply as previously, 3 minutes. Who wants to start? Irina, do you want?
Yes. Okay, thank you. Actually, I have quite a lot to say, but I tried to stick to the main points, so to keep the timing. Thanks a lot for the interesting presentation and the report. So it was very, very nice to read also your work. And yeah, some good things that I just wanted to highlight. That yeah, I liked your selection of the baseline. That it is a clear baseline to having all electric vehicles was one decision, but it's good to be able to capture the effects of automation, as you also said. And then especially I also liked that you provided these estimates on the energy demand of these technologies related to AVs, because that is very difficult to be able to quantify. And yeah, there's not much information available so far, but I think this will be at least a good point of reference for the future until there maybe becomes more data available. But what I found a bit challenging when I was asked also to reflect and wanted to reflect on your results compared to what I've been doing or we've been doing in the L3 Pilot and HI Drive projects, assessing the energy demand and CO2 impacts of automation and the automated passenger cars in our case. And I found it challenging or had to do some modifications of the results and some interpretations to be able to come to comparable results. But what I can say that even though we used very different tools, so different simulation tool and different driver models and different AV models, still I think that the results go in the same direction. So there was, when we compare the baseline scenario only with manual vehicles and then this automated scenario with slightly different automated vehicles, but I think comparable, then the direction is at least the same, and also the magnitude of effect seems to be similar. So I think that was very interesting, and it would be also, and generally, would be nice to discuss more about these results from different studies, because also one question was if I think that these results can be generalized, and I wanted to say that no results from any simulation study should be generalized as such, because they're always so dependent on the model and the assumptions, and that is often kind of neglected or not considered enough in the interpretation of results. But yeah, I think also this quick exercise that I did showed also that there can be still common findings, and I think it's important to look at if you take results from different studies together, then maybe we can come up with more robust conclusions than just single studies on themselves. So we always need to consider, when interpreting simulation studies, then the specific assumptions, of course. One thing that, or another thing that I wanted to highlight also, your choice of network was interesting, or this simulation model of 3 hours, and maybe we can discuss later. But I would like to know also what your thoughts is about the generalization. So how far can you generalize from this network? We took in L3 Pilot high drive a different approach, or tried to go through many different possible scenarios, so speed limits and traffic volumes. And I tried to compare also these conditions to each other, but it was not so easy. So one part also what I would like to highlight is this what has also been mentioned in this conference, the common evaluation methodology for CCAM. So I hope that in the future this method will make it easier then to compare also results with common indicators or common kind of framing for the assessments.
Indeed, thank you, Elina. Who's next? Who wants Christian? Yeah.
Okay. So on behalf of the CCAM Partnership, and with my second head I wear for BMW, I would also echo what have been said by my colleagues. We are very thankful having this study. It's a very good foundation on this topic of energy consumption of CCAM mobility. I will keep rather a bird's view on my evaluation. And as said before, for sure, we have to be careful when combining policies, mobility policies, with technology aspects and assumptions. Definitely there are some pros, but there are also some cons. We have to be a little bit careful on the overall policy message. I think you said it, Dimitris, before. I mean, this is pretty clear, I believe. And what was really interesting for me, and also a big takeaway for me, is the evaluation on the ACC performance. Was really interesting to see all the differences and in graduation of the traffic flow potentials. And yeah, and in general, for sure, this was also said before, ADAS and AD needs energy, but on the other hand, we get something in reverse for the society, and this is again all about the policy and the mobility systems. And that's clear. The whole digital transition needs a lot of energy, and it's clear that we need to find solutions to have CO2 neutral energy best possible. That's also clear from my point of view. And to end here, it was also said by Christian from Bosch, the energy consumption from the point of view of the vehicle manufacturers is at the core of the development targets because it's connected directly to the battery costs, to the battery capacity and the battery range. So it's a key selling argument for our customers, and it's highly competitive for the customers and for internally for us cost-wise as well. So I would not be concerned at all that the trends would not point into the right direction in the next years. So yeah, I'm very positive concerning the outlook of the trends, and yeah, therefore I give back to you. Thank you.
Thank you very much, Vincenzo.
Thank you, Andrea. Well, first of all, I start from we had no chance of meeting, but I was a delegate for the university in the board, CCAM board. So before you became, so one of the attempts, a small contribution I tried to give in the CCAM to the CCAM ecosystem is that when we, of course, introduce new technologies into a system, we must observe the system. And so I think this is particularly true in this case, because as far as I understand, the most important saving from this system comes not directly from the technology. Of course, we have an increase in the consumption, but comes from the benefit of these technologies. So the reduction in traffic flow, and this is, of course, is very, I would say, very tricky. Because the experience tells us that the traffic system are very lively system in which, of course, we do not need to focus on the technology, on the vehicle itself, but of course, on the interaction of vehicles. But the properties of traffic emerge from the interaction of the vehicles, but also the interaction with the infrastructure. And of course, the level of demand. So just to connect with the previous answer, definitely, the study cannot be transferred because every system has its own specific features and works in different way from others. So this is not to diminish the value of the study. I would say that if I were a reviewer, I would have really easy time because the study is very well conducted and. Usually I hunt for assumption, unreasonable assumption or biased assumption. I couldn't find anyone here. And so, but going back to the, let's say, to the tricky point is that maybe if I have time, I would give a nice example. Almost 15 years ago in Naples, we had a preview of what does it mean to move from a fully chaotic, manually driven traffic to a, let's say, partially automated driving. Because we introduced on the motorway of Naples in automated section speed enforcement systems. So people were fined not to overpass the speed just in one single location, but if the average speed, of course, exceeded the speed limit. And so what we observed from one day to another, when we switched on the system, it was a dramatic, a really stunning decrease in the speed. And of course, also a big homogenization of speeds. And so we expected really also a reduction in emission. But from a traffic point of view, what we observe is that there was a specific point in which we have every day a severe bottleneck. And with this introduction of this technology, the bottleneck really eased, so almost disappeared. But what we did not expect is that a bottleneck appeared downstream, because of course it was hidden by the previous one. And so, because the previous one, to some extent, attenuated the flow, which could not reach at really high rate the second location downstream. And when we removed the first bottleneck, another bottleneck appeared. And so this tells us that you cannot be, let's say, myopic or blind on the technology itself, but has to be integrated into the system. And so this calls to let's say, a collaboration between technologists and traffic and engineer, infrastructure manager, because only in this way we can really reach these goals. And maybe another stupid example is that, for instance, if we would like to basically save energy, of course we could use whatever eco-driving algorithms we try to smooth, so because consumption is function of the variance of acceleration, we would have a very smooth acceleration. But this in turn, if this acceleration profile are too smooth relative to the deceleration profile, we would get an hysteresis loop, which means dispersing platoon, and so a decrease in capacity, and again, an increase in energy consumption. And so, if I understand well this, and the main benefit here are given by the effect on traffic flow. But we have to be so very, very careful on this, and we have to work to be. And the very last thing, another important point I found is that we have an equity problem, because the cost, the higher cost of energy is all on technology. But the benefits are for the whole community, because if it is true that the traffic flow is released and the total energy consumption is reduced, also for people who manually drive, we are saying that the whole cost of this operation is on the AVs and not on the whole community. And so in this case, we need maybe policy intervention, incentives. And again, we never experienced, let's say, a previously congested road that after intervention which improves situation, that we never see that we do not have, newly generated traffic. And so again, we need intervention on policy. So policy is fundamental. So collaboration between traffic, so technologists and traffic engineer, manager of infrastructure, but also, of course, the intervention of policies is crucial. And
thank you very much. Now I would like to take some reactions from the floor, if any, comments. Also, the panelists can comment, except Vincenzo, on the others. Okay, it's good. We are different, all different. I'm also Italian, by the way. All right, so any comments?
Yes, Christian. Just a comment. We all know we have the Vision Zero in Europe to drive down dramatically injuries and people killed in traffic. So an idea would be to have a rough estimate on these traffic flow effects, avoiding accidents, incidents, injuries, and in addition to that, the economic loss due to congestions. And this setting into the relation to the energy would be very interesting, I think, also for policy deciders.
Yes, I wanted to comment on the energy demand still. So, while I agree that it has an effect, and every single thing should be lowered that can be lowered, but we still should keep the big picture in mind. So, if I now, you can correct me if I'm wrong, but if I calculated correctly from the results, I got the impression that for the the share of the auxiliaries of the AV technology of the energy consumption depends a lot on the speed. So in urban speeds, it would be much higher per kilometer driven than in motorway speeds. And for common motorway speeds like 120 or 130 speed limit, it would be like 3% or something of the energy consumption or energy demand of the AV. So I think much larger effect there would have the speed. So lowering the speeds would have much more effects than focusing on this few percent of the energy demand. And I was focusing or referring to the this, not the prototype, but the second one, this enabled system.
Thank you. Now, if there are, yes, there is someone I don't see. Yes, the microphone is coming. Yeah.
Thanks a lot. I'm Jane Lappin. I'm from the US, obviously, from my accent. And I want to build on Christian's observation about Vision Zero and automated vehicles, because not only do we have a high probability that the automated vehicles will have fewer crashes themselves by virtue of their ability to avoid conflicts and mitigate the impact, the severity of conflicts and impact. We improve the safety for the whole fleet. So it isn't just that individual vehicle that becomes safer, but rather the flow. It's like the herd immunity effect of vaccination. And that would make an interesting next step in your modeling.
Thank you. Are there any other comments from the floor? Otherwise, I will ask a challenging, my last challenging question to the speakers, to the panelists. They have 30 seconds each, and we would like to know what kind of action you would take once you will be home in your organization, following what you have heard, or what kind of new idea you got. So who wants to start? Okay. Elina?
Yeah, first of all, I would like you all to take an action when you get home and take a look at the common evaluation methodology if you have not already done it. But yeah, myself, I will take a closer look at your report. I tried to read it all, but did not. Maybe I missed some of the details. But yeah, so what I would like to do, I cannot do alone, but I maybe can take some initiative in that, cooperating more with among the different projects in research, also on this energy demand, because what we can do now, or only thing we can do is simulations if we want to study these energy demand effects of automation, and then the more varied data we have, the more we know about that.
Thank you, Elina. Christian?
Yeah. First of all, as CCAM chair, I would like to, or will take this study back to our partnership, to our cluster leaders for further discussion on the further research needs. This would be the first action. And the second one, I would, with my BMW colleagues, discuss the outcomes of the study with specific respect to the ACC, looking where BMW exactly is in the field of best practices and traffic flow. Thank you.
Thank you. Vincenzo, 30 seconds.
I will ask Costas and Biagio to send me the slides so that I can use them in my lecture.
Good. Thank you very much. We are approaching the end of this nice session. I just would like to grab your attention to the composition of the two panels. You may have noticed that my colleagues in JRC, and I look at in particular Biagio, were clever and smart enough to have a representative from academia, representative from research centers, and representative from industry in each of the two sessions. So it has been very, very, very rich. So different opinions, even though very much aligned. And then I would like to explain you just in 1 minute why I ask each of them to tell us one action, what they do, because this report at the end is a piece of information which could be new, hopefully new for not all, but new. But if it stays a piece of information, it's not useful. So any piece of information becomes knowledge at the moment you make use of it. And now we have some suggestions. Now I would like each of you that coming back can think of an action. What to do? You will get this report, and then what you do with this. But with an extra complexity. So information, when it is used, becomes knowledge. Information, when it is used in a responsible way, becomes wisdom. So allow yourself to become more knowledgeable. Allow yourself to become wiser. And now, join me in the big applause for all the speakers. Christian, Ben Batain, and Dimitris, and Elina, Christian, Vincenzo. Very good job. Many thanks to my colleague from the JRC for the study and for the presentation. Many thanks to Biagio, because Biagio worked in backstage in the preparation of this, and he will have to work for the report. So many thanks to Biagio and his colleagues. And many thanks to all of you for your patience. You've been great. Thank you.
Thank you very much to you, to our moderator.